Hi, Peter Allen from Columbia University, and I'm here at this workshop to show you a little bit of some work we've done on an application for tactile sensing, which is grasping, which is the most traditional application. And also talk a little bit about what we might need in the future to make tactile sensing even a better modality than it is now. So let me share my screen. First, let me present MAT, which is multi-fingered adaptive tactile grasping by deep reinforcement learning. These are my co-authors, and this is a closed-loop grasping system using binary contacts only with tactile sensors. It solves the visual occlusion problem in that often when you're trying to grasp something, the hand gets in the way, you can't see at the very end, and you have errors. It's robust under calibration error, which we'll show you. It works with cluttered, unseen objects. Works with multi-finger hands with full degree of poses, not just top-down or simple binary grippers. And it's a simple add-on to a vision grasping system. So let's talk first of all about open loop grasping, which is the most common kind of grasping. Works pretty well. We did a system recently, has full degree of freedom vision grasping in clutter, 92% success rate with cluttered unseen objects. Uses reinforcement learning. It's general across arbitrary high degree freedom hands. It's direct sim to real transfer. Works pretty well. So it works almost. And again, with 92% success rate and all these things, it works with arbitrary hands, but it still has an 8% error. Okay, you can see some examples of that here. Here you see a slipping off a cup, and here you have calibration error on the bottom, and it misses it with a different hand that we're using. So there are multiple causes of why things fail when you try to pick them up without closed loop. And calibration is number one. If you're doing a machine learning, you may have a problem with optimization, sim to real transfer, the object's pose, if it's transparent, if it's reflective, if it's disturbed. These are all issues that create problems for open loop grasping. So what we like to do is finish the last mile closed loop grasping. And here we see Bohan Wu, who's one of the authors of this paper. And he's going to show you exactly what he's going to do. He's blindfolded, but yet he's able to pick things up. So here he's going to go through a whole bunch of movement and pick these items up. And he adapts his hand once he makes an initial guess, and he moves it around and moves his fingers and finds a stable grasp. And this is something humans can do very effectively. And there he gets the last object. You can see what the human is doing. He's actually coming to a guess of where this thing is, and then he's adjusting his grasp around that. And that's exactly what we want to do with Matt. So here we see an initial guess of where this is, which is based upon a vision system, but then at that point it becomes purely closed loop grasping using tactile feedback as the tactile sensors respond and let us know how we can find a better grasp if we're off by a little bit. So how does this work? Well, here we have a scene with cluttered unseen objects, and we have an initial guess of where this grasp should be as we approach it. We're going to get tactile contacts, and they're going to go collect observations, do binary contacts, find the joint angles, tactile contact, and then we have to do an action. Do we reopen the fingers because it's a bad grasp? No. Do we lift it because it's a good grasp? No. What do? We want to close the fingers by a small delta, which is going to emulate closed loop control, and try to get this into a situation where we can get a better grasp. And we slowly flow it, and new tactile contacts will show up, as you see in the lower left. And we're collecting those observations. And at this point, we can go back through these questions and say, okay, we have a new set of tactile contacts. Should we reopen the hand? Yes, we don't like what we have, so we'll reopen all the fingers. And now we'll adjust the end effector orientation and position to try to optimize on what we do know about the tactile context. And then we can go through the system again, and then I try to close it through these small incremental deltas, and we'll get a better grasp. And at this point, we want to say, okay, we've got a lot of tactile context now. Should we reopen? No. Should we lift? Yes. And now we'll lift it out. So that's the idea. And here we can see how we've actually implemented this in a machine learning sense with direct sim-to-real transfer. We have a pi-bullet simulator that has cluttered scenes, and we're just learning through tactile context how to pick these objects up. What's nice is it only takes 8 hours to multi-thread simulation training. We have 300 plus objects, 1,000 plus random cluttered scenes. We don't have a GPU because there's no vision. It's a very simple sensor set. So we can compare this to the open loop system we saw earlier, and you can see that the improvements, they are there, and you can see that that 8% is being eaten away by tactile. But it's even more impressive when you look at things like calibration error. So we have experiments under grasp perturbation where we have here a scene, and what we're going to do is we're going to perturb these items. As you can see, we have initial grasp pose generated by the pixel antenna system, and then we're going to move that guess 5 centimeters and see what happens, and see if we can pick it up using a tactile adaptive system. And you can see here, it's able to adaptively find a good grasp, and it does that for these other objects. And if it doesn't find a good grasp away, then it will adapt to it, as we can see. And again, using the finger control, reorienting the gripper, and deciding whether to lift or not, or open the fingers, we can come up with a strategy which is pretty effective. And clear the table right out. So basically, if we have a 5 centimeter error, you can see that in the real world, the performance degrades very fast with a closed-loop system. With a closed-loop tactile system in blue, it works very well and keeps the performance high, regardless, because it's adaptive. And typical calibration error, you can still see of 1 centimeter, you can still even see improvements. So we can also use any other kind of grasp. It doesn't have an overhead grasp. We can find grasps that are consistent with these tactile contexts and what orientation we come from. So the key takeaways from this is that this is closed grasp using binary tactile context. We don't have any force control. We don't have to worry about grayscales. We just say, are we in contact or not? And that's enough in this system with the resolution of these sensors to do this job. It solves a visual occlusion problem, as you can't see when you get close and you're trying to pick up something and there's error. And it works with cluttered unseen objects, as you can see, multi-fingered hands. It's a simple add-on to vision grasp system, and uses direct sim-to-real transfer. And these are my co-authors again, and this is just a recap of it. But what I'd like to talk now is the future tactile system, what we need, what we don't have. And from doing this work, one of the things that we found very compelling was to have non-planar sensors for multi-fingered hands. Most multi-fingered hands will have curved surfaces. We need more coverage on the fingers and the palm, so you can hit with the back of your hand and get responses. It's not just the flat pads of the fingers, which is nice and it works, but it's limited. Second is to have believable and non-hysteretic force sensing. That would be a big, big win, and it's a very difficult job, but it is something that will allow precision grasping tests to occur. Knowing how much force you're exerting is very important, especially on deformable objects or articulated objects. Moving ahead, whole arm body coverage is, I think, a key, and that as humans, we have that. We have tactile sensing in a sense all over our bodies, concentrated in the hands, but we do have touch sensing on other areas. Scalability and redundancy are very important. And that relates also to the physical robustness factor. I believe physical robustness is more important than precision and resolution. So you may have a coarse-grained tactile sensor, but that works all the time, and you can bounce it off a table, etc. That's more important than having high force control and very accurate sensors. So those are things to keep in mind as we go on and build better tactile sensors in the future. So thank you.